Hello and welcome to today's webinar. My name is Peter Viscuso with VoltDB. Today's webinar is entitled Tapping Big and Fast Data, Achieving the Competitive Advantage. So thank you for joining us today. Before we begin, just a little bit of housekeeping on webinars. Many times people will ask, will they be able to get the slides and a recording to the webinar? And the answer is yes and yes. Usually in about 24 hours, you'll get a follow-up email that includes a link to the recording and a copy of the slides. There are a lot of people online, so the lines are muted, but we do want to have Q&A with our presenters. So if you would, use the Q&A window, which is located kind of on your screen, and type in your questions as we go. We'd be happy to take those up at the end. As I said, the lines are muted to cut down on noise, but we encourage your participation. Okay, I'm going to introduce our speakers. We're fortunate to have with us today Ryan Betts. Ryan is the CTO of VoltDB. He's also one of the original developers of the VoltDB product. He's been with us from the beginning and even predates the beginning. Ryan's, prior to joining VoltDB, had worked at IBM and Lucent Technologies before that. And then we have Walt Maguire. Walt is the Chief Field Technologist for HP Vertica. He's got 27 years of experience in analytics and data technologies. He says he practiced data science before it had a name, worked with big data when big meant a megabyte, and has been part of the movement ever since. So welcome to our speakers, Ryan and Walt. I'm just going to review the agenda quickly, and then I'm going to turn it over to Ryan. We're going to start with talking about corporate data architecture for both fast data and big data. And that falls into two categories, really: VoltDB's role in this architecture and HP Vertica's role. You'll hear from Ryan on VoltDB and Walt on HP Vertica. We'll come back at the end, and Ryan will talk about the value of the combination of VoltDB with Vertica, and then we'll open it up for discussion and Q&A. So with that, I'm going to turn it over to Ryan Betts. Ryan?
Thank you for the introduction, Peter, and thank you everyone for attending. And thank you, Walt, for joining us. I'm really looking forward to being able to present this kind of point of view, what we see in the marketplace as emerging architecture to solve both fast and big data applications. And I think having Walt on the phone to discuss this with me today is going to be a lot of fun. So if we could go to the next slide. What we've seen is as technology and application patterns have evolved, very naturally, the database technology that supports those applications has grown to meet the new challenges. And I think it's fun to point out that STONEBRAKER, the founder of both Vertica and VoltDB, has been present with technology appropriate to the application pattern change at each of these inflection points, creating products like Ingress, Postgres, Streambase, Vertica, and VoltDB. What we're beginning to see now, however, as big data and the Internet of Things drives a new set of data management challenges, is a need to combine a heterogeneous set of solutions into a total architecture capable of supporting both fast data and big data. I'm going to walk through that architecture for you. Next slide. As you solve big data problems, it's not uncommon for practitioners to walk through a very common workflow, and we see this pattern over and over and over again. In fact, today, before this webinar, I was visiting with a prospect, and they again described exactly this same pattern to me. The first challenge that organizations face is simply collecting the data that together kind of comprises their big data set. This is often log data, input data, metrics, events, recordings of invoices or sales. It's a large set of information that's distributed across their organization, and the first challenge is to collect it. Once it's been collected, or once more likely a pattern of periodic and regular collection has been established, the next task is to begin to explore that corpus of information. You're exploring, looking for clusters or trends or opportunities. Typically, exploration is based around a concept that you think you know some pattern that would allow you to create value from this data, right? Allow you to create business value, additional revenue, or reduce cost. You're just not quite sure what it is or if your hypothesis is true or not. I think this exploration phase is one of the many things that's really driving the demand in the market for data science expertise. Once you've started the exploration phase and kind of proved out some hypothesis, it often results in some kind of analytic process. You want to be able to produce a report or a summary on a standing and formal basis of the hypothesis that your exploration has put forth. And so that's really the third phase: collect, explore, analyze. And finally, having gone through all of that work, there's, of course, a natural need to act against the result of that analysis. And it's really through this action that you finally realize perhaps the monetary benefit. There is a huge learning benefit, a deep wisdom benefit. You can learn a lot about your organization, a lot about your customers, about your product, about their satisfaction through the analytics and the exploration phase. In the action phase, however, we're really talking about the opportunity of engaging customers as they are interacting with you. So a real-time environment that is predictively and actively engaging customers with opportunities to customize experience, to personalize recommendations, to offer appropriate upsell, cross-sell opportunities, or from a resource utilization perspective, to best utilize expensive operational infrastructure, whether that is network infrastructure and least cost routing kinds of scenarios, or if it's to realize hardware reduction cost by using appropriate fast data technology for perhaps very scalable authorization applications in telecommunications networks or even in ad serving. So what's interesting is as you walk through this sort of common kind of problem life cycle, collect, explore, analyze, and act, there are tools that are best suited to each of these phases. And we can see these tools divide roughly into a big side and a fast side. Now, there are many ways that you could draw divisions through this particular workflow, but I think highlighting from a data management perspective the requirements of fast data versus big data is very interesting. On the big data side, you absolutely need a combination of storage, and you need a columnar database capable of applying modern, fast, kind of real-time analytic reporting, right? And the big data side, your fundamental problem is how much data can you store. The benefits of columnar compression is absolutely critical to making that affordable. And the second question is how fast can I scan that data? Because the type of work you're doing on the big data side is usually an analysis of a large volume of information all at once. So you have a lot of data and you have relatively fewer queries. The fast data side is really the inverse of that. And because how you physically organize data in a database matters a lot to the performance and capabilities of the tool, being a very different problem, the fast data side necessitates a very different architecture at the database level from the big data side. So on the fast side, it's not about how much information or how much data can you store. It's about how fast, with what low latency, and with what high throughput can you respond and interact with the data that's arriving at your organization. So can you turn very fast kind of streaming event-oriented feeds of information into kind of traditional transactional applications where for every event or for every session you're capable of making a decision that's utilizing the analysis derived from the big data applications and responding back to that event or alerting off of that event in order to try to create value in real time. Next slide. So when we look at the requirements for fast data, I think, and I'm going to focus on fast data here. I think the requirements for big data are a little more familiar, and I think Walt's going to do an excellent job at walking through that. So let me focus for the moment here on the fast side. What are the requirements? And this is kind of a slightly new concept, but one that we're seeing develop very rapidly in the marketplace, and developers and technical executives and architects are commonly asking me, what do I think is the right set of functions for the fast portion of this total architecture? Well, first of all, the fast side has to have the performance capability to ingest this data. Right? You simply have to meet the performance requirement. That often looks like tens of thousands or hundreds of thousands of events or requests per second, often each of those requiring responses in some single-digit number of milliseconds. Right? These are data feeds that are often in line with customer experience, either as a customer is playing a game or interacting with you at a point of sale, or perhaps passing an iBeacon, right? And you want to be able to push information to them relevant to their demographic, to their user, and to their very specific location, right? These are all performance-oriented kind of applications. And so meeting that performance requirement is the first piece that you have to meet for your fast data architecture. The important point here, though, is that performance is really just a first requirement. In order to write meaningful decision and ingest and analytics-oriented fast data applications, you also need the capability of making per-event decisions. I'm using the word decision here, but what a decision really is in the context of data is a transaction. Right? A decision is looking at the current event, kind of comparing that to its historical context, understanding the perhaps the segmentation or the strategy that you're going to derive based upon the big data analytics, combining all of that information into a single transaction where you can reach an optimal decision and calculate a response. In order to make real-time decisions, you absolutely need to be able to hold state. You need to have a state of a way of persisting information. And you need to be able to have a system that supports rich computation against that persisted state. That's what I mean when I say make per-event data-driven decisions. Additionally, these real-time data feeds create operational challenges. And it's important that you can build operational monitoring against them. Sometimes we call this streaming analytics. Sometimes people refer to this as applications like streaming MapReduce. But what we see commonly is that there is a set of BI or dashboard applications, perhaps monitoring the health of the data providers or the performance kind of quality of service of APIs that are connected to this infrastructure. Being able to implement real-time analytics against these real-time feeds is very important. The fast data side is, as we spoke at the beginning, absolutely architected towards the performance of decision making. It's not about how much data it can store. Right? That's really a problem best solved by the very different technology on the big data side of this picture. And so integrating the fast side with the big side is absolutely critical. And that integration goes in two ways. Potentially you want to use the fast side to filter or to sessionize or to enrich with metadata, dimension data, the data feed that's arriving, and archive that essentially real-time transformed feed to your OLAP system. Right? So having a high-speed, distributed, scalable way of passing information from the fast side to the big side after it's been decisioned and perhaps operated against is critical. Additionally, if you're going to make decisions in real time that have value, it's important that you be able to have the context of the analytical results from the big data side. So the big data side has to have some way of feeding the results of its analytical reports, the output of those reports into the fast data side in order to provide the context for the decisions that need to be made. Next slide. So there are a number of paradigms being put forth on how to solve the fast data problem. And of course, at VoltDB, we have a strong opinion about the right way to do this. The three different approaches being put forward are also different ways of looking at the problem. And I'd like to discuss that for a moment. There are a set of vendors that are putting forth essentially in-memory OLAP solutions to fast data. I believe that's absolutely incorrect. The value of OLAP is on the big data side, and simply reducing by some minuscule amount the time to that OLAP analytics isn't worth the duplication of effort. It's also not a technology that allows real-time decision making, and so it's the wrong technology for this fast data side. A second option being put forth is stateless streaming architectures. The proponents of these architectures are arguing that real-time data is really just about database coordination, right? That it's really just about a message bus and some basic analytics that you can hard code if that's what you need. We think the problem is much richer than that. I think that the real value of the fast data side is about personalization. It's about real-time fraud detection. Essentially, it's about the ability to make per-event decisions. And a pure streaming architecture that's stateless, enriching data, making decisions against data, transacting against data, or generating responses against data, these are applications that are foreign and extremely difficult to write on top of streaming architectures. So we believe very firmly that the right architecture for a fast data problem is a database architecture. You need to have a transaction-oriented database that's capable of the performance requirement, right, the ingestion requirement, and that's also enables developers to write interesting transactional decision-oriented applications against those fast event feeds. Next slide. So I'd like to talk about VoltDB in the context of a fast data solution. Next slide. In about 2008, Mike STONEBRAKER and his team of researchers looked at the OLTP problem space. By this point in time, they had reinvented OLAP in the form of Vertica. They had worked on streaming problems in the form of Streambase. They had been well on their way of specializing databases to slightly narrower application spaces, and by giving up general purpose functionality of a traditional database, they were able to achieve 10 to 100 to even 1,000 times performance increases, enabling a new set of applications. When they looked at the OLTP space, really the last kind of bastion of the traditional database vendors, they asked themselves, what's changed since 1970? And the answer is that a lot has changed. One, these database applications now fit in memory. When legacy databases, traditional row store databases were designed, that certainly was not the case. Secondly, these modern transaction processing applications are absolutely driven by middleware and by applications. It's no longer an operator at a green screen making your airline reservation. It's a set of highly coordinated middleware applications that are interacting with you and with a large number of third parties and with the airline reservation system, with your hotel reservation system, with your automobile reservation system, right? All working together as a series of very fast applications. So next slide. When you look at what you can do to make a better database, to make a better transaction processing database specifically, you first have to understand what are legacy databases so bad at. We know that they don't scale. We know that scaling a legacy database is a consistent pain point for developers. Anyone who's faced that challenge understands the difficulty of scaling a traditional database. We know that they aren't capable of dealing with high concurrency workloads, and we understand that they're often not particularly latency performant. Right? They can have very variable latency responses. A legacy database was taken and instrumented, and a TPC new order transaction, a very common benchmarking transaction, was run against it, and the instrumentation was used to determine what percentage of time that database spent actually running user SQL, and what percentage of time was overhead. The only thing the user cares about is, are you evaluating my query? Right? Anything else that the database is doing is essentially overhead from the user's perspective. It turns out that roughly 10% of the time, 10% of the database's execution cycles were spent running SQL. The other 90% all went into managing durability, to managing concurrency control, and to managing deadlock detection. So I think that's phenomenal if you just stop and think about it, but it's not surprising if you consider the ways in which computer architectures have changed since the 70s and 80s when these traditional databases were built. Computers now have more cores than we can shake a stick at. It's actually very difficult sometimes to saturate all the cores of a computer. If you've written high-performance distributed software, you've probably looked at an application and wondered, why are my CPUs so idle? Right? We have so much CPU that sometimes we struggle to consume it all. We have lots of memory. It's not at all random to have hundreds of gigabytes of RAM in a single server. We solve our problems now through scale out, not through scale up. And we design systems that are easily virtualized for cloud deployment. So if we go to the next slide, these are all assumptions or all observations that are reflected in VoltDB's architecture. So when you kind of think through this and you design a database specifically to remove the legacy limitations, you end up with something that looks like Volt. You have a high-velocity in-memory system. It stores all of the data for computation in memory while maintaining a durable and transactionally consistent copy of the data on disk for disaster recovery. It's capable of scaling horizontally to handle an almost arbitrarily large number of transactions. Customers have put together 16 node Volt clusters capable of processing millions of transactions per second. You can keep a relational ACID compliant SQL interface. You don't need to throw away the interfaces that have been proven at being reliable and efficient for building database applications. You don't need to get rid of transactions. You don't need to push transaction management into your application space. And I think we've seen that the popularity of SQL is only growing. If you just look at any data management ecosystem, you'll see that more and more SQL implementations are being created on it. In fact, some of the most recent Hadoop announcements from large Hadoop vendors are all announcements about SQL on Hadoop. So even in one of the least kind of relational models, SQL is still being applied. So it's important to keep that benefit. And of course, you need a system architected to scale out in the cloud. So if we go to the next slide, I'd like to talk about a feature of VoltDB that's unique and that helps it uniquely position into the fast data capability space. As we discussed, as you're solving fast data applications, it's really critical that you have a way of connecting the data that's arriving from the network or from sensors or from these machine-to-machine devices or from web click streams or from ad networks to capture that and to send it to an OLAP system after you've had the chance to decision and respond to it. To solve that problem at VoltDB, almost since day one, we've had an export connector. And specifically, the very first export connector we wrote was an export connector to Vertica. Showing the combination of VoltDB and Vertica together has been something that we've been working on and doing for users and prospects for many years now. VoltDB has the capability of streaming data at gigabit Ethernet speeds on a per server basis, scaling that across a cluster to Vertica. And Vertica, of course, has the wonderful capability of ingesting that raw data feed and getting it very quickly into its column store where it's able to do real-time reporting and real-time analytics against what we would term historical data, even if it's maybe only seconds or minutes old. The export connector from VoltDB to Vertica is a very rich and productized capability. I think over half of VoltDB's customers are using some form of export. They're realizing this combination of fast data and big data. They're using VoltDB to decision against their data streams, and they're using it to connect and capture that data stream to a downstream target. Vertica is an optimal example of that. When you put all of this together, go to the next slide, what do you see? So what do you see from a performance perspective? So we've run VoltDB versus the YCSB benchmark. YCSB is a popular NoSQL benchmark. I wish that it showed off more of VoltDB's SQL capabilities, but it's a very capable benchmark for showing kind of cluster database performance for a lot of the modern NewSQL and NoSQL systems out there. And so we're happy to run it and present what we think are world-leading numbers. We ran this benchmark in both AWS and in IBM SoftLayer. We weren't attempting a direct SoftLayer versus AWS comparison. The point here, though, is to show that VoltDB is capable of essentially world-class performance either on bare metal in SoftLayer, the red line, or in a very default AWS implementation. Note that, for example, in SoftLayer, we built a 3-node cluster that was capable of hitting 1,000 YCSB kind of B workload scaling requests per second. And we scale that horizontally as the cluster grows in size. All of these transactions are receiving responses at 99th percentile latencies of roughly 2 to 5 milliseconds. So a pretty astounding performance profile. And at VoltDB, we leverage the performance profile that you see here along with our transactional benefit and our tools like our export connectors to Vertica to help people realize an application stack that combines fast and big and completes the full big data workflow from collect, explore, analyze, and finally to act. Some different examples of what those actions look like, if we go to the next slide, when they're kind of instantiated in VoltDB. We see broadly 3 different patterns of applications. So I think developers, and at least I as a developer, I'm always looking for patterns and trying to understand how do I repeat a pattern and what are really the unique and important patterns in my application. At VoltDB, we see three large kind of styles of application, and we can discuss them in turn by thinking about the data flow through the database in each of these different patterns. So in the data pipeline case, there's a set of incoming inputs to VoltDB that don't expect responses. So there are a lot of sensors, for example, like infrastructure smart meters or kind of RFIDs that aren't really waiting for a response. The applications we write against these input feeds tend to be pipeline-oriented applications. We are using VoltDB to do correlation of events, to filter unneeded or duplicate RFID inputs in order to understand in real time how to enrich data, perhaps with location data, software version data, right? The ancillary kind of dimension and metadata that we don't want to repeatedly send over the wire over and over again. Right? We can store that in VoltDB and enrich that on a per event basis. And then invoke the pipeline aspect of this, meaning that we flow the data from the source to VoltDB, perform these enrichments against it, can perform real-time analytics against it, and then pass the resulting feed downstream to the next stage of the pipeline, Vertica, for example. We also see applications that are doing real-time analytics, in this case using the combination of VoltDB's in-memory and PP-SQL, along with our ability to do pre-aggregation of streaming counters and leaderboards and things like that to provide real-time insight into data feeds. I want to stress that when you're doing rich reporting analytics, VoltDB is really the wrong tool. At that point in time, you absolutely want Vertica, right? You want to be able to use all of the power of a columnar OLAP system. What I'm talking about here is cases where you can specifically know in advance that there are a certain number of aggregates or groupings that are important to you. Perhaps you need those groupings in order to make real-time decisions. You want to understand at a per session level or as you're generating responses to applications exactly what's hot right in this minute, or if a session has been fully completed, or how many users are immediately online for a load balancing application. Right? So these are analytics that are very much tuned towards that real-time requirement. And finally, the third pattern is really the traditional database application for transaction processing, and that's a request-response pattern. I think the easiest explanation of this is applications that require a fast authorization. Can I place this call on a mobile network? Do I have permission to display an advertisement against this campaign? Are there sufficient funds available? All of these types of applications are traditional request-response applications, only when you look at them in a fast data sense, they have a performance profile that you might not expect you could solve with a traditional database. Right? That's, again, where the power of VoltDB really comes through and allows you to use the familiar technologies of Java and SQL and ACID transactions, but also provides the performance capability of writing applications against for real-time data feeds. So that brings me to the end of this first section. I'm going to hand this off to Walt to describe a little bit about the big side of this and the Vertica side of this, and then I'm going to come back and give an example of what VoltDB and Vertica look like together when they're kind of composed into one application. So Walt?
Awesome. Thanks, Ryan. First, can you hear me all right?
Yes.
Okay, great. So thank you for the intro. You know, we've known about Vertica's been very closely tied with Volt for a number of years. In fact, Vertica in the early days shared the same office space with the Volt team, and so you know we definitely been in touch with the team for some time. What I'd like to do now is transition from the fast data part of the discussion to the big data part. You know, we've talked about kind of the use cases for Volt. And what I'd like to do now is take, say, 15 minutes or so and give everyone a perspective on the Vertica platform and just what we mean when we say big data. So, case in point, big data means, in our case, we have numerous multi-petabyte clusters running globally today. I was at one of my customers on the West Coast last week who reported to me that their primary fact table is now about 7.5 trillion rows. And their analysts typically get results from that table with sub-second response time. So that's just a flavor for what we mean when we say big data. what we've seen emerge in the market over the last few years is data has steadily moved from the back office closer and closer to the customer. So if you think back to, say, 1994, we're all putting in ERP systems and CRM systems. 1999, we're all putting in data warehouses, and maybe we're starting to automate the sales force. Say in 2005, we're all putting in these really fast analytic platforms like Vertica to do large-scale analytics. Now what we're getting is a lot of people who are saying, I need to take that predictive model, I need to put it on a tier which is immediately adjacent to my applications so that I can score in real time, and I still have the workhorse behind it. I can push the model out, and I can provide a very, very rapid response time, very low latency measured in milliseconds, to a very large number of concurrent users on, say, a travel application for upsell and cross-sell. It's a very, very common emerging use case we see today. So let's talk about Vertica for a few minutes. The way I describe Vertica today is I say it's three things. First, it's a distributed high-performance computing platform, which happens to be a database, and it's an important concept to remember as I talk more about this. That means that we began with a very purposeful strategy. We built a distributed system which solves a number of problems that you have to confront when you're dealing with loosely coupled hardware and networks of unpredictable quality and so on. We initially built it as a database, so ACID compliant, tables and columns and rows and referential integrity and all the things that people know and love about databases. It uses SQL, so the language you use to work with it is SQL. It has a set of enterprise features, and we reinvented the storage engine. So one of Dr. STONEBRAKER's visions was that row-oriented storage was insufficient to meet the needs of the changing world of data. So we reinvented a storage engine. I'm going to talk more about that in a few minutes. That does some very important things for us, which enable the scale and the performance characteristics of the system. It makes it very fast and extremely good at scaling from small to large. So the second thing Vertica is, it's a software platform. So we built it as software only. We didn't tie it to hardware appliances. And it's designed to scale. So start as small as you want and go as large as you need to go. A number of customers I've worked with started with 3 nodes, and a number of those today are running clusters measured in hundreds of nodes. I think I just talked with one of them who told me they were at 400 nodes and planning to grow further. And it can be optimized for an appliance as well. So we've delivered it in various iterations as an appliance through HP. We've got various partners and such. So it's very amenable to embedding. Now, these were just means to an end. We made it fast. We made it scale. That's nice, but in the end, that's not enough. The whole purpose was to build an analytic platform. So to that end, we have a series of built-in SQL analytics, things like pattern match, which is the best described as a between-row grep, things like standard statistical algorithms, and so on. Time series analytics to simplify joining of uneven time series and so on. It's extensible, so a set of APIs for users and customers and VARs and resellers to extend it with analytics written in Java, extend it with analytics written in C, a variety of types of analytic functions, so you can extend it with user-defined loads to open up the doors to other kinds of formats and so on. That's laid the groundwork for us to extend it in interesting ways, which begin to create data transparency. So you can extend today the scope of visibility of Vertica to beyond just the Vertica cluster. We can actually point it at external things, and you can start looking at those file systems and treat them as forms of storage transparent to the analyst. And finally, innovations in marketplace. So we are commercializing some technologies from HP Labs. We released a few of them already this year. One of them is called Pulse. Pulse is an in-database sentiment scorer. So in the context of SQL, your analyst can now take, say, a tweet and extract the topic of the tweet and extract the sentiment of the tweet. And this is the point of what we've been doing. We made it scalable and fast, easily accessible via SQL, and now your analyst can sit at the console, access the data irrespective of location, and start to do things that maybe were very hard to do 3 years ago, like sentiment scoring. So a little more about the technology. When Vertica rolled out, we threw out the row-oriented storage engine. So the very first thing I tell people is column orientation. There's some very simple math here. If you think about say a fact table that has 100 columns, on disk I'm going to store all those values next to each other for that row. That's a very sort of Postgres and Oracle, and everybody's been doing it that way for many years. The first iteration of column orientation is I can take that and I can store just the columns I need and access just the columns I need. So in the case you see here, I maybe have something where all I really want is a very fast query by date of stock trades. And so you can very quickly figure out that I've eliminated all the I.O. on the other columns, and I'm only reading the 3 I need. This is what I call column 101. That's the beginning of column orientation. Once we do that, now we can do some very interesting things. So in Vertica, there's the notion of when we store it, we also sort it. When we sort it, now we can do some very interesting things in the columns. So what you see here is a couple of algorithms that we can bring to these columns. So let's say, for example, I'm storing 1 billion rows of that stock ticker information on disk. The first column is date. A date is very low cardinality. If I'm storing a year of data, I have about 365 distinct values. In Vertica, I can run length and code that. And what that means is it means I can store the date, I can store the length of the run of the date, and then I can store pointers to the next column at the beginning of the end range of the next column. So you can very quickly figure out I've just achieved enormous compression on that column. I've taken 1 billion rows of dates, and I've compressed them down to 365 distinct values with a little bit of overhead. This is an example of the I.O. performance that you start to see with something like Vertica. Once I've acquired a date in that query, now I have what amounts to an index lookup on the next column. And that column also is compressed. So all these benefits start to accrue since we built the platform ourselves. What we didn't do is we didn't take a row platform and add those features on. That's a very subtle difference, but it's worth knowing as you look at other vendors in the space. The next thing we did was we made it scale. And we made it scale in ways that are not going to introduce bottlenecks. So the Vertica architecture is that I can deploy, say, 3 systems, 3 2U, HP. Of course, we'd like to say HP because we're HP, but you can buy Dells. I'm going to put them on the same network. I'm going to install Vertica, and I have a multi-terabyte cluster. If I need to expand that cluster, I rack up another server, I run an administrative command, and I have a 4-node cluster. Queries will parallelize across this. So we distribute the data. We have a variety of fault tolerance mechanisms to protect the data. And what will happen is when you run a query, it will actually light up across this system. This is sort of fundamental, right? We made the column engine go fast in terms of storage on node. This brings in the ability to scale to arbitrary sizes. So there's a concept called the projection in Vertica, which is very relevant to the columnar discussion. When we developed the column storage engine, we loosely coupled the logical schema from physical storage. So what that means is when you run create table in Vertica, Vertica is going to do 2 things. It's going to create a stub, which is we call it a logical table, and that's all the user ever needs to know about. Underneath it will create a thing called a projection. The projection initially will have all the columns that are in the table. It'll make some assumptions about sort and compression and distribution, but you can create additional projections. You can create projections with a subset of the columns. They can be sorted differently. We can use the fault tolerance mechanism of redundant projections and for inverse sort orders and so on. So once we've done this, now we've created what I call the go fast button. If your users need something to go faster, you can create projections. You can change projections on the fly without downtime and modify the performance characteristics of the system. Another piece of this that's worth knowing about. All of you who've been database people probably started to scratch your heads when I said that. We didn't want you to have to invent it yourself. So we wrote a tool called the Database Designer. The Database Designer will take your queries and your data. It will then find the set of projections which optimize performance of those queries on that data. You can deploy them automatically, or you can have it write out a script and review the script and deploy the script yourself. So this is fundamental to the performance characteristics of the system, and it's what allows it to scale out tremendously. Let me talk for a moment about customers and use cases. people are using us for a variety of things. What we're finding is there are two ways of thinking about it. One is by industry. The one that we see a lot of is by analytic use case. So on the right side there, you see customers are using us for a variety of advertising-related behaviors, advertising-related activities, promotional testing. You see a lot of clickstream analysis with Vertica, a lot of customer and marketing analytics. We see a lot of fraud detection. We see a lot of, in financial services, we see ticker data analysis, and hedge funds do some interesting things with Vertica. We see a lot of fraud detection and financial monitoring. In healthcare, we see behavioral and clinical analytics, patient records, clinical effectiveness, and so on. The customers there, I probably have worked with 10 or 12 of those myself, and I know them very well, all using Vertica in similar types of ways. Very large-scale analytic warehouses that allow them to bring together very disparate forms of data and work with it very quickly, because the challenge with analytics has never been really a good path of analysis. For decades, there have been people who can do analytic inquiry very well. The challenge has been allowing them to do it faster, because analytics is a very iterative process. So what we see very often in the Vertica install base is the process that used to take 4 weeks. They might run a SaaS job, have to sample it, pull out a data set, crunch the data set, go back, ask IT for the full-scale data set, schedule a window to run the job on the full-scale data, get the full-scale data, decide it's wrong, iterate it, run it again, and then they have it right. It took 4 weeks. Vertica, that becomes a 1-hour process. They can do it in database. They can do it very quickly. So these things become transformational for a lot of our customers. Industry-wise, today, Vertica's got a footprint across a number of things. So this is a flavor for industry-wise, how we've gotten traction. A lot of traction in media, a lot of traction in consumer web, particularly in the West Coast of the United States. We've got an increasing install base in health and life sciences. We do business very actively in the retail industry, a lot of financial services and energy, and some public sector and security and fraud detection analytics as well. So that's a quick overview of Vertica. Of course, there's a lot more to it than that. But what I'd like to do at this point is turn it back over to Ryan to talk about how these things go together.
Thank you, Walt. I always, every time I hear you describe Vertica, I always learn something new or kind of have a new thought. So I certainly appreciate the chance to listen to that. It was very informative. Thank you. So if we can go to the data architecture slide again, let's set up just a quick example showing what it looks like when you can combine fast and big together. So next slide. We see this pattern a lot, and as I had mentioned before, a majority of VoltDB applications are really deployed in combination with OLAP systems, and we see that across vertical. So if we go to the next slide, let's look at kind of a very simple abstract example that references what Walt was speaking to when he was speaking about applying scoring in real time to a very high concurrency or a very large concurrent number of users. So in this case, we're going to use VoltDB for fast, we're going to use Vertica for big, and we're going to use bidirectional connections. We're going to use VoltDB export to flow data from the real-time stream from VoltDB to Vertica. And very much equally important, we're going to use a VoltDB extension, a VoltDB Vertica UDX piece of code that will allow Vertica to natively invoke the VoltDB bulk loader to, in an MPP fashion, stream analytic results from Vertica to VoltDB. The end result will be a high-level example showing per event personalization using real-time data in combination with historical scoring. So go to the next slide. A few months ago, we did a webinar with a VoltDB customer that was describing how they use real-time user segmentation in order to improve revenue generation from free-to-play games. In their case, they take their user base and they divide it up into roughly 100 to 200 different segments. So each segment has 1 to 2% of their entire user base in it, and they apply per segmentation strategies in real time. So as the user is playing the game, depending upon their demographic, their location, how many times they've played the game before, all of the different criteria that go into determining user segmentation, they will modify the game or tweak the game to further encourage that user's engagement. So if you're playing the game and you're playing very rapidly and you've been playing for a long time, they may make the game a little bit more difficult when you change levels from level 1 to level 2 as you advance through some game. And it turns out that by being able to tweak the game, by being able to, in an automated way, tune the game to the user segment and to their current gameplay style, that they can increase per game revenue by 30% or more on certain user segmentations. So this is really an example that shows the combination and the value of being able to combine big and fast. So on the big side, you would use Vertica or a tool like Vertica in order to produce that user segmentation model. And very importantly, as Walt was describing, you would use Vertica here in order to explore, to understand what that segmentation model would be. I think Walt said that analytics, that this kind of real-time analytics is absolutely an exploration or an iterative process. I think that we all understand that pretty intuitively, but we're so unused to seeing that in our database tools that we don't often approach analytics in an interactive way. But if you can sit down and begin asking questions, one question leads to the next, and you begin almost to have a conversation with your data. But that conversation is only possible if the analytics are fast enough, right? So that kind of power allows you to derive something like a user segmentation report from a set of theories or hypotheses into an analytic that can be formally repeated at very high performance. So that's the kind of work that you might be doing in Vertica. That user segmentation model could then be loaded into VoltDB using the Vertica VoltDB UDX extension. This means that from a SQL-only interface without writing any other code, you can take a formal report from Vertica, a formal analysis, and you can have the result set or the tuples of that report shipped to VoltDB. Notice that in this case, you're only taking the results of that analytics. Right? So Vertica in this case will have terabytes or petabytes of event data that was generated by this game platform. But the only data that VoltDB needs on the fast side is the few 100 million rows that represent the different users and their segmentation assignments, right? A substantially smaller amount of information that we can store in memory. Having put that information in VoltDB, in memory, and in our database architected for fast requests and responses, we can begin to serve personalization requests from the gaming platform. The gaming platform, as the user plays, can send opportunities to customize user player experience, opportunities to upsell or cross-sell, to offer the user the magic sword they need to maintain their engagement for a simple 99 cents, and really achieve two things at once. They improve the player experience. They make literally a better and more enjoyable game, and by making the game more enjoyable, they also drive revenue. On the VoltDB side, they're not using Volt to do deep analytics or to explore the data or to produce this user segmentation report. Instead, they're using Volt's in-memory capabilities to generate responses to these personalization opportunities back to the gaming platform in latencies that fit into the user experience. So as the user is advancing to one platform of the game to the next, they can have a personalization opportunity and generate a response in a few milliseconds that can be integrated into the gameplay experience without disrupting the user's kind of overall perception of the performance of the game. This is a really common pattern. We see this kind of real-time scoring across verticals. I think the gaming example is a nice one, and it fits into an area that both Volt and Vertica have some focus in. So if we go to the next slide, I want to look one more time at what happens when you put these two very different but very compatible technologies in combination. VoltDB is in memory. It's storing gigabytes to perhaps small terabytes of data. It's processing tens of thousands to millions of requests per second, and it's giving responses to these requests at latencies that are usually single-digit milliseconds. And it's capable of connecting the new data flow to Vertica and capable of receiving Vertica analytics back. On the Vertica side, you have really the opposite performance profile, right? You're storing terabytes to petabytes of historical data. You're still absolutely able to query the database in sub-second times, but you're not doing that hundreds of thousands of times per second at low latency. Rather, you're approaching that from more of an analytics perspective. And the way that these two systems are designed to access data really enables each to be best at its own function. So that brings us to the end of our discussion. As people think about what questions they might have, we would of course be happy to answer. I would like to say that and encourage you to try both Volt and Vertica. The final slide shows you how you can obtain a copy of both to evaluate.
Great.
So Peter, I think I will hand it back to you.
Yep. Thank you, Ryan. Thank you, Walt. And we do have a number of questions. Not a lot of time left, so we'll get right into them. One of the questions was, can I evaluate Volt in the cloud? You see you can, and if you just go to the download link there, you'll see how. Another question was, are the benchmark results that Ryan referred to available online? They are. If you go to the VoltDB website under resources, there's a data sheet there that documents the benchmark for your use. Ryan, there was a question about, could you talk about a use case for Volt in financial services, and if you could do that pretty quickly.
Sure. So in financial services, we're seeing people use VoltDB to build post-trade applications to take what were end-of-day compliance checks and turning them into real-time per-trade checks. So that's something that we'd be happy to discuss in more detail, but that's a very quick example of one place where you can use VoltDB's transactionality and its ability to transact against a very fast event stream, or in this case, two event streams, a tick stream for price and a fulfilled trade stream, and look for real-time compliance violation. Thank you.
And then there was a question about migrating from SQL Server to VoltDB. Ryan, this is for you, obviously. Could you talk about kind of how to think about that, how difficult it is, et cetera?
Yeah. I think anyone who's attempted a database migration understands that it is usually a challenging prospect. What we find as people migrate applications from a legacy system to VoltDB, that there are usually 2 points that need to be considered. The first is that in many cases, the legacy database they're coming from was not a distributed system, and so the user needs to think a little bit about how they might structure, partition, or distribute data in VoltDB to leverage the fact that it can scale horizontally. And secondly, VoltDB represents its transactions as a combination of Java and SQL, and oftentimes there's some translation required from a legacy application. I have seen applications that were extremely difficult to port, that took a long period of time, and I have seen very large applications where developers have ported them over a weekend. So I think it's really something that differs by specific use case and by technology, and I think to some extent by developer experience. So unfortunately, I can't provide a very concise answer to that, but that's an overview.
Nope, great, thanks. I like this question because it's kind of a combination fast data, big data question. To be able to make real-time predictions, don't you need to relate fast data with big data, for example, to build the model and compare with real-time events in real time?
Right, absolutely, and I think that's the value of the combination. So when I speak to the need to bring analytic results from your historical system, from Vertica, into your decision-making system, VoltDB, that's what I mean, right? So you need to be able to combine multiple pieces of information together. You need the historical context. Someone I was talking to once phrased this as you need your wisdom, right, which I really like that metaphor, and that comes from your analytics system, right? That comes from Vertica. At the same time, you need to be able to act against the incoming event stream in combination with that wisdom, right? And so that's the kind of the combination of data that we're seeing.
Yep, great, thanks. I'm not quite sure of the question. I'm hoping, Ryan, you'll understand it, and Walt. It says, does VoltDB convert NoSQL data into SQL before exporting to Vertica, or Vertica convert into SQL? Who performs the conversion? What about the other data flow direction from Vertica to VoltDB? Does that make sense,
in
Ryan?
the case, it does. I understand that. So in the case of VoltDB to Vertica, VoltDB's export framework provides an opportunity to convert data between formats in a well-abstracted way. And in the case of Vertica to VoltDB, the UDX integration allows you to either load an exact matching schema from the Vertica result set to VoltDB. It also allows you to invoke in a very efficient way VoltDB procedures on the VoltDB side so that you could do translation at the point of insertion. So I think that would actually be a webinar interesting unto itself. It might be an interesting topic to follow up on later, Peter.
Great. Okay, thanks. I think the last question is for you, Ryan. Can the database be partitioned in Volt? Is scaling as easy as adding nodes?
Yes. So VoltDB distributes data into what we call partitions, other people call shards or replica sets. We distribute data horizontally, and we allow the cluster to be expanded while online, while servicing user workloads without ever sacrificing any serializable isolation or ACID property. So I really like the way that Walt described having built a proper distributed system first, and then incidentally it happened to also be a killer database, and that same kind of DNA exists in Volt.
Great. And Walt, anything to add to that for Vertica?
No, I think Ryan summed it up pretty nicely.
Great. Okay, and with that, we're out of time. I want to thank all of our participants for dialing in. As I said earlier, you'll get a follow-up email with a copy of the slides and a link to the recording. Thank you very much for that. And to our speakers, thank you, Ryan. Thank you, Walt. Very much appreciate you guys joining us today. And with that, we'll say goodbye. Take care.